So if at all you are performing a task, if you are performing a task, right, what you will check whether after performing that particular task, what you will check is that result has been obtained or not. Yes or no, right? The same way, using a control system, you are implementing a particular task and you have to check whether the result has been obtained or not. So how will you check it? Using steady state error, right? By calculating steady state error, you will check whether under steady state conditions that your task has been accomplished or not, right? The same way, the steady state error for the steady state parameter, most important steady state parameter in your steady state analysis is nothing but steady state error. So we have to calculate steady state errors for various inputs, right? So just put that in, steady state errors, right? Let us say you have a negative feedback system, something like this. This is the forward path transfer function, right? This is your feedback path transfer function h of s, and they are connected in a negative feedback configuration like this, right? So if r of s is your input and c of s is your output, where is error calculated? E of s. E of s will be your error, and this b of s is feedback signal, right? So therefore E of s is equal to what? E of s is equal to r of s minus b of s, right? So how would you get b of s? B of s is the output of h of s. The input to h of s is c of s, which means r of s minus h of s into c of s, right? So how are you getting c of s? C of s is E of s multiplied by g of s. That is r of s minus h of s into c of s is E of s multiplied by g of s. G of s into E of s, right? Just segregate the terms containing E of s so that you can calculate E of s. E of s into 1 plus g of s h of s. G of s h of s is equal to what? R of s, right? Therefore E of s is equal to R of s divided by 1 plus g of s h of s. This is E of s, right? The steady state value of error is nothing but steady state error. So E of s is equal to R of s upon 1 plus g of s h of s, right? Steady state value of error is what is required for you. This is error. You have obtained E of s, right? So steady state value of error means ESS is defined as limit t approaching infinity E of t. Limit t approaching infinity E of t. What is E of t? E of t is nothing but the time domain version of E of s. Time domain version of E of s. Therefore, this will be found out using the the final value theorem. That is limit s approaches 0, s into E of s. You can find out this using the final value theorem, right? Therefore, ESS is equal to limit t approaches infinity E of t, that is equal to limit s approaches 0, s into E of s. Therefore, ESS steady state error is equal to limit s approaching 0, s into R of s upon 1 plus g of s h of s. So this is the generalized expression for your steady state value of error. The steady state value of error could be found out using this generalized expression, right? So if at all you do not remember the future things which we are going to discuss, you can simply remember this, and within minutes you can calculate this, right? So even if you don't remember this, that's not a big problem. Upon solving 1 or 2 problems, you'll easily memorize this. That's not a big problem. Is it fine? Is it clear, everyone? Yes. So on what all factors is your steady state error depending? Right? Your steady state error is depending on the type of input as well as the open loop transfer function. Right? So your steady state error is depending on the steady state error of the system is depending on type of input as well as the open loop transfer function. So we have to generalize this for various inputs as well as various types of open loop transfer functions, right? For what type of open loop transfer function, how the steady state error is going to be, right? So all these factors we just need to simply derive it, right? So let us look at the steady state errors for various inputs, right? So let us look at the steady state error for a unit step input, or else generalize this for generally step inputs, not just a unit step input, for step inputs. So the steady state errors for step input, ramp input, parabolic input, all these have to be calculated, right? So the first input we are going to see is, can anyone tell me why aren't we calculating steady state error for an impulse input? So we are giving an impulse input only at t is equal to 0, and after t is equal to 0 there is no input present at all. There is no input present at all, and what for do we want to calculate steady state error, right? So if at all a system doesn't have steady state value for an impulse input to be 0, right, then such system is not a stable system. So you will come to understand when we discuss about stability, you will come to understand all these things, right? So for a step input, if we are providing a step input, which means r of t is equal to, see, I am taking a generalized step input, r of t, it is not a unit step input, it is a step of magnitude some a, right? So r of t is a times u of t. What about r of s? What about r of s? R of s is equal to a by s. So see here, r of s is a by s. Then what about the steady state error, right? Steady state error ESS is equal to limit s approaching 0, s into r of s divided by 1 plus g of s h of s, that is equal to limit s approaching 0, s into a by s upon 1 plus g of s h of s, right? So this s gets cancelled, you will be left with limit s approaching 0, a by 1 plus g of s h of s, right? So see here, simple thing here is, if you put s is equal to 0, 1 is constant, 1 is not depending on s, right? A is constant, a is also not depending on s. The only factor which is depending on s is g of s h of s. So this limit can be written as something like this: ESS is equal to a by 1 plus limit s tends to 0, g of s h of s, right? A by 1 plus limit s tends to 0, g of s h of s. So this limit s tends to 0, g of s h of s has been given a simple name called Kp, where Kp is called as positional error constant, 1 plus a by 1 plus Kp, right? Therefore, the steady state error for a step input is a by 1 plus Kp, where Kp is equal to limit s approaching 0, g of s h of s. This is called as positional error constant. Positional error constant, right? So the reason why it is called as positional error constant is your step input is called as position input. Step input is called as what? Position input. Step input is called as position input, right? So by defining the level, right, by defining a level at the input 1, 2, 3, 1.1, 1.4, like this, we are defining the position of the output, right? And that is the reason why it is called as a position input, right? So if at all you see the error for a position input, it is a by 1 plus Kp, where Kp is equal to limit s approaching 0, g of s h of s. This definition, all these error constants which we discuss here are very important for your examination point of view, right? So just, this is very important, please memorize it. You can easily memorize it. We'll study ample number of we'll solve ample number of problems from this, right? The steady state error for a step input is what? It is a by 1 plus Kp. It is just a by 1 plus Kp, right? So let us look at the steady state error for the next input, that is velocity input, right? So if you are continuously varying the position, you are defining a level, you are defining a position by giving this particular input, right? Whereas now you are giving a velocity input. Velocity input means you are continuously changing its position, right? Which means a ramp input, right? You are changing its position at a constant rate. So R of t will be is equal to some a into t times of u of t. This is your ramp input, which means R of s is what? R of s is a upon s square. Therefore, ESS is equal to limit s approaching 0 s square s into a by s square upon 1 plus g of s h of s, right? This square and this s gets cancelled. You are left with limit s approaching 0 a by s into 1 plus g of s h of s, that is equal to a by 1 plus limit s approaches 0 s into g of s. So this is ESS is equal to a by 1 plus limit s approaches 0 s into g of s h of s, right? So kV, it tends to 0. This is s. Limit s approaching 0 s plus limit s approaching 0 s into g of s h of s. Yes, very good. Thank you. Right? So what should this be? It is a by limit s approaches 0 s will be 0, right? A by limit s tends to 0 s into g of s h of s, right? Therefore, ESS is now a by kV, right? A divided by kV, where kV is equal to limit s approaching 0 s into g of s h of s. That is equal to what? Velocity error constant. It is called as velocity error constant because the input which we have provided is velocity input. Velocity, right? So your position input, position has been varied at a constant rate with respect to time, and that is the reason why it is called as velocity input, right? So please take a note of this. So the third input is acceleration input, that is parabolic input. So what is R of t for a parabolic input, for a generalized parabolic input? R of t should be a times t square by 2 u of t, because unit parabola is t square by 2. Unit parabola is t square by 2. T square by 2 multiplied by a, it is R of t. Then R of s will be is equal to what? R of s will be is equal to a by. So do you people had a doubt why it is called as unit parabola? Right? Unit step, its coefficient is 1. Unit ramp, its coefficient is 1. Whereas unit parabola, its coefficient is 1 by 2. Why isn't it called as half parabola and why is it called as unit parabola? Do you people had this doubt or not? See, what is unit step? U of t. Integrate unit step, what you will get? If at all you integrate unit ramp, you will get t square by 2 u of t. By integrating unit ramp, we got this. That is the reason why it is called as unit parabola. The only reason is by integrating unit ramp, we got this. That is the reason why it is called as unit parabola, right? So if a is something other than 1, this is no longer unit step. This is a step of magnitude a, right? This is a unit ramp of magnitude, this is a ramp of magnitude a. This is a parabola of magnitude a, right? A indicates magnitude of your input, magnitude of step, ramp or parabola. The for parabolic input, let us calculate the steady state error. ESS is equal to limit s approaching 0 s into a by s cube divided by 1 plus g of s h of s. So that is equal to limit s approaching 0, this s this cancels with square, right? A divided by s into 1 plus g of s h of s. That is equal to what? Sorry, s square into g of s h of s. It is a by limit s approaching 0 s square plus limit s approaching 0 s square into g of s h of s. So this will approach 0, right? So we are left with ESS is equal to a by limit s approaching 0 s square g of s h of s, right? This is ESS is equal to limit s approaching 0 s square g of s h of s. You can call it as a by Ka, right? Where Ka is acceleration error constant. Acceleration error constant. Ka is equal to limit s approaching 0 s square g of s h of s. This is the value of Ka. So acceleration error constant Ka. Why is it called so? The reason is the input is acceleration input. Input is acceleration. The rate of change of position is increasing at a constant rate, right? So that is why it is called as acceleration input, right? The position is accelerating. Is it clear? So is it easy or else is it difficult to remember all these formulas, right? If for a step input, the error is a by 1 plus k a by 1 plus kp. For a ramp input, error is a by kv, and for a parabolic input, error is a by ka. That's it, right? So very simple. So let us go with a generalized tabular form, which will give you a good idea of how the error varies for what type of system, right? So just construct a table, just as I do here, right? So this table we are generalizing to get some sort of idea. It will see what idea we are going to get through this, right? So any transfer function we have, right? So it has a general structure, right? So even it is g of s h of s, right? This g of s h of s is going to have a general structure. What is that structure? A numerator polynomial of s upon a denominator polynomial of s, right? So the numerator will be something like this. KDC, I am taking the generalized form, 1 plus STA, 1 plus STB, so on, divided by S power Q into 1 plus ST1, 1 plus ST2, so on, right? So this will be G of S, H of S, right? So if type of G of S, H of S is 0, let us say type of this is 0, right? Type 0 means Q is equal to what? Q is equal to 0, right? If Q is equal to 0, it is S power 0. S power 0 is what? 1, right? So S power 0 is 1. So let us calculate Kp for type 0 system. Kp, what is Kp? Limit s approaching 0, g of s, h of s, right? So if we put limit s tends to 0 in this, what do we get? If we put limit s tends to 0 in this, what do we get? Yes, we'll get KDC, very good, right? So Kp for type 0 system is what? KDC, right? What about Kv? What about Kv? Kv is limit s approaches 0, s into g of s, h of s, right? If we multiply KDC with s, where s tends to 0, the result is what? 0. Very good. Very good. Right? What about Ka? Right? Just substitute the limit in this. Limit s approaching 0, s square g of s, h of s. S square, see here, s square multiplied by all this. If you put s is equal to 0, 1 plus 0 into 1 plus 0, divided by 1 plus 0 into 1 plus 0, right? This is 0, right? 0 multiplied by anything? 0, right? So you're going to get 0 in this. So now let us calculate all these things for type 1 input. So sorry, for type 1 system, right? If the type number of the system is 1, it is s power what? S power 1, right? S power 1 means simply s. S will have to be there here. So what is the value of Kp for type 1 system? For type 1 system, what is the value of Kp? 1 plus 0, 1 plus 0, all these are 1. 1 plus 0, 1 plus 0, all these are 1. Right? Kdc divided by 0. Something divided by 0 is infinite. Very good. So it is infinite. Right? What about Kv? What about Kv? Kv means S into this. This S and S gets cancelled. You will be left with yes. Yes, very good. It is Kdc. Right? What about Ka? Ka. Ka is 0. The same way for type 2 system. For type 2 system, this is infinite. This is infinite. What about this? This is Kdc. Right? For type 3 system, all the three are infinite. Right? Once we get these constants, we can get the errors for step input, ramp input as well as parabolic input very easily. Right? So what is the error for a step input for type 0 system? For type 0 system, what is the error for step input? For a type 0 system, error for step input. Yes, it is not 1. A by 1 plus Kp. Right? Therefore, ESS is equal to A by 1 plus Kdc. For ramp input, it is A by, for ramp input type 0 system, A by Kv. Infinite. Error is infinite. Right? For parabolic input, again, the error is infinite. For step input type 2 system, error is A by 1 plus infinity. A by 1 plus infinity. That is 0. For ramp input, A by Kdc. Right? For parabolic input, it is A by 0, that is equal to infinite. Yes, very good. Right? So for step input again, for step input and type 2 system, it is again 0. A by 1 plus infinity, something upon infinity 0. Right? So for ramp input again, it is 0. Whereas for parabolic input, it is A by Kdc. Error is A by Kdc. Right? So what about the errors for a type 3 system? All the constants are infinite, which means all these are 0, 0, 0 only. See, what is Kp? Kp is limit s tends to 0 g of s h of s. Jitendra, please concentrate here. Kp is limit s tends to 0 g of s h of s. Right? So just substitute the limit s tends to 0 g of s h of s. Right? For a type 0 system, type 0 means no poles or zeros at origin. Right? So this s term is vanished. Right? So for type 0 system, if you put s is equal to 0, 1 plus 0 into 1 plus 0 into so on in the numerator, divided by 1 plus 0 into 1 plus 0, so on in the denominator. So overall it is 1 in the numerator and 1 in the denominator and multiplied by Kdc. Right? For type 0 system it is Kdc. For type 1 system, what happens is it is Kdc by s. Kp is equal to limit s tends to 0 g of s h of s. If you put s is equal to 0 in this, something upon 0, right? Something upon 0 you will get infinite. So that is what we have given it here. Right? Even for type 2 system, it is Kdc by s square into so and so. Right? If you put s is equal to 0, it is something upon 0, you will get infinite. Like that we have calculated all these values. So is it clear, everyone? Did you people note it down? Yes. See, one observation here if you observe, there is a little observation here. See, for step input, for type 0 system, error is some finite value. For step input, type 0 system, error is finite value. You have increased the type of the system by 1, then the error became 0, right? From there, the lowest value of error possible is 0 only, right? Error was finite, later on it became 0, 0, 0. As type increased, the error has decreased. Whereas for ramp input, let us look at the case of a ramp input. For ramp input, type 0 system, error is infinite. Very large value of error, that is infinite, right? Whereas for type 1 system, you have increased the type of the system by 1. If you have increased the type of the system by 1, what happened to the error? From infinite, error became finite. You have again increased the type of the system by 1, right? What happened to the error? Error became 0. Whereas the same case for parabola also. As you are increasing type from infinite, see, for type 0 and type 1, error is infinite. From infinite error, the error had come to a finite value. As you have increased the type again, the error had became 0, right? Which means there is an observation here. As you are increasing the type number of the system, the steady state value of error is decreasing, right? As type number increases, steady state value of error decreases. So this is very, very, very important observation, right? As type number increases, steady state error ESS decreases. So just solve this particular problem. The steady state error of the system shown in the figure for a unit step input is, right? This was a problem given in GATE 2014, right? So if at all you look at the block diagram, I can simplify the block diagram like this. See here, this is the block diagram. 4 divided by s plus 2 upon 2 divided by s plus 4, right? So this is the block diagram. In this, g of s is 4 by s plus 2 and h of s is 2 by s plus 4. Therefore, g of s h of s is equal to what? Is 8 divided by s plus 2 into s plus 4, right? So Kp, positional error constant, is Kp is limit s approaching 0, g of s h of s, that is equal to limit s approaching 0, 8 divided by s plus 2 into s plus 4, that is equal to 1. If you put s is equal to 0, it is 8 divided by 8, that is 1. Therefore, steady state error ESS is equal to 1 by 1 plus Kp, that is equal to 1 by 1 plus 1, that is equal to 0.5. You should get 0.5. So 0.5 is the answer given by the gate board. 0.5 is the answer given by the gate board. But see, there is a contradiction here. What is error? We have dealt with steady state error in the previous classes while analyzing for transient analysis also, right? Steady state error, E of t, limit t approaching infinity, E of t is defined as what? It is the difference between output and the input, right? So limit t approaching infinity, r of t minus c of t, right? But the error we have calculated here is, see here, this is r of t, this is b of t. The error E of t which we have calculated here is E of t is equal to r of t minus b of t, not r of t minus c of t. This is what we have calculated here. We have calculated E of t is equal to r of t minus b of t. This is not error. Error means r of t minus c of t, right? So the approach whatever we have studied till now, that is valid only for unity feedback systems, right? So this approach is valid only for unity feedback systems, but this is not valid for non-unity feedback systems. As far as non-unity feedback systems are concerned, the approach is completely different. but your gate authority, which they have conducted this exam, right, in 2014, they did not accept the answer other than this, right? They have accepted if the answer is 0.5, which means they are going through the procedure which we have learned till now, right? But that procedure is valid only for what systems? Only for those systems which are of unity feedback, right? If the system is non-unity feedback system, then you have various literatures, right? In Norman S. Nice, in this literature, they have just converted the system into a unity feedback configuration, right? So we can convert any feedback system into a unity feedback configuration. After converting it into unity feedback configuration, they have found out the error, right? So they have used this approach in this. Whereas if you refer Benjamin C. Kuo in this, right? So the dimensions of output as well as the input might be different a lot many times, right? So they have manipulated the dimensions and they have given a valid approach, a 100% valid approach, right? Of course, I can say Benjamin C. Kuo has given 100% valid and 100% correct approach, but that is not followed by your gate board. So you have to follow what your gate board follows in order to get marks in gate, right?